your cell is filled with easy water, and easy water is critical for everything. And we don't have enough easy water. The cells are either dysfunctional or pathological. Number one, if you don't have enough easy water, your cells are not functioning. Number two, the cell's electrical potential is a consequence of easy water. Your healthy cells are minus 50 to minus 100. Cancer cells are minus 10 to minus 15. They don't have very much easy water. They're basically non-functional or reduced function. And also, it's been shown like 50 years ago. What is the cancer cells divide all the time? They just keep dividing. In normal cells, what is the condition for allowing cells to divide? Well, it was found like 50 years ago that when the cell potential goes from minus 50 to minus 100 down to close to zero, it's a signal. It stays there. It's a signal for the cell to begin dividing. It has to stay at that. But cancer cells are there all the time. Therefore, cancer cells,
of course,
keep dividing.
We have been given the scientific knowledge, the technical ability, and the materials to pursue the exploration of the universe. To ignore these great resources would be a corruption of a God-given ability.
Hi everyone, welcome back to my channel. If you're new here, my name is Stefan. And today for Stefan Burns Live number 5 on the topic of water, we have Dr. Gerald Pollack, who runs the Pollack Lab at the University of Washington and a prolific researcher, has written quite a few books on water and some of the other facets at play in regards to water. There's the fourth phase of water, his second book, Cells, Gels, and Engines of Life. And then there is also, Muscles and Molecules, and countless research papers. So, Doctor, thank you so much for joining us today. And if you could start off with just perhaps what initially intrigued you with water. Like, some people looked up at the moon and they wanted to be an astronaut. Like you saw water flowing out of a tap and you're captivated.
No, it wasn't. It wasn't exactly that. It was a combination of circumstances. So, you mentioned my book, Muscles and Molecules. I had been in the field of muscle contraction for quite some years, studying the molecular mechanism, how the proteins of muscle interact to produce force and motion. And it was about, I was to pick up a colleague from the airport who was coming to work in my lab, a Hungarian colleague. And in the drive from the airport to my home, he said to me, there's a really important conference going on in Hungary in the next few months. You should go there. And I wondered why he mentioned it. He said, this conference is in honor of a Hungarian biophysicist who passed recently, and his fields were number one, muscle contraction, and number two, water. And so they've recruited a bunch of people to come and speak on the issue of water, which is not my field. But he said they have nobody to speak about muscle contraction. And his ideas were non-mainstream, just like yours. So you're exactly the right person. So why don't you go? Okay, so I went. I didn't know what was to befall me, but I turned out to be mesmerized by what I heard. And what I heard was from the dozen or so people who had been invited to speak about water. And primary among those was a guy named Gilbert Ling. And Gilbert Ling was no ordinary scientist. He was in the first cohort of scientists drawn from China to come to the US after World War II. They looked all over China and they selected 3 people. One was a physicist, a chemist, and he was the biologist. The physicist went on to win a Nobel Prize, although he became actually more famous for marrying his translator. He was approaching 90 and his translator was in her early 30s. And in China, that became the talk of the town. And there was even a rumor that she got pregnant. Well,
Oh,
anyway, so the
his
physicist
water is working.
yeah, well, uh, the physicist got a Nobel Prize, and a colleague told me that the chemist got a Nobel Prize, and Gilbert Ling should have won at least 2 Nobel Prizes for all of his contributions. These were amazing people who came. The first cohort, 1948, and it didn't take too long before Gilbert Ling started studying water in the cell. And Gilbert had an idea um, that really impressed me um, about the water in the cell. He said it's not liquid water; it's a kind of structured water. And at the time I didn't know very much about what's meant by structured water, and what he was talking about was water in which instead of liquid water, where the molecules are randomly disposed and bouncing around a fierce number of times per second or even per femtosecond.
Depending on their temperature, right?
Well, it depends on temperature, but even at room temperature, ordinary water, at least the common theory of ordinary water is that the molecules are bouncing around, so-called thermal motion, Brownian motion.
Yeah.
That's liquid water. Um, but he said, no, it's not like that. He said the water inside the cell, it turns out the water he's talking about exists outside the cell too. That comes later, but he was focusing on the cell. And he said the molecules are lined up. So the molecules are like dipoles. If dipole is like a bean with a plus at one end, minus at one end. And I think most would agree that the water molecule is like that. And he said they're all lined up like soldiers at attention with the plus of one attached to the minus of the other. And you can imagine how they'd be stacked. And so I heard him talking about that, and I was impressed not only by the idea, but also by the evidence that he had presented, massive amounts of evidence. And I realized at the time that he'd already written 3 or 4 books on the subject. I was even more impressed by the people who had been invited, who had evidence to support Ling's point of view. My head was swimming in this stuff. I couldn't believe how interesting and how important this was. And early on, a colleague of mine told me this was in the field of muscle contraction. He was working in my lab. He said, you ought to consider water because nobody talks about water, and muscle is mostly water. It's like 70% by volume. But if you actually start counting molecules, line them up and count one by one, more than 99 out of 100 molecules in the muscle and other organs too are water molecules. And
A tremendous amount.
it's tremendous amount. Yeah. And you'd think, what's going on here? How come 99 out of 100 molecules are not doing anything? Or in fact, in the case of muscle contraction, they're not even there. So the theories of muscle contraction, I'm not sure how aware you are, but they presume, if you look at any of the models that you will see in the textbook and such, they presume that it's working in a vacuum. There's no water. And if there is water, it's different from if there's no water. So this colleague he was an Israeli colleague, and he kept bombarding me with questions about water. So I had back of my mind that, water might be important. And there I was in Hungary, listening to all those people talking about the centrality of water.
And what year was this?
This was like more than 20 years ago, perhaps 22, 23 years ago.
So right around the millennium.
I'd say, yeah, I can't recollect. It was around then, because my first book on the subject was 2001, so it must have been late 90s that
Okay.
I was. Yeah, so the first book. Well, I came back to Seattle, and my head was spinning with intriguing information, because I knew if this guy was right, everything else is wrong. Because all the biology, physiology, biochemistry is built on the idea that the water is ordinary water in your cells and my cells, and that molecules are free to move around by diffusion, osmosis, everything. But if Gilbert Ling was correct, then that was not the case, and you had to start from a different premise. And I was, of course, intrigued by that because, after all, we're in the process of finding truth, not mimicking what everybody else believes, but penetrating down to ground truth. So it intrigued me. On the other hand, I felt that I was maybe gullible, too easily persuaded by evidence that seemed captivating. So when I came back to Seattle from that conference, I got one of Gilbert Ling's books, and I gave the book to a few of my postdocs who I thought were particularly talented. And after reading it, they came back to me, and their view was unanimous. They said, "This is absolutely amazing, and if correct, it is going to change everything." So naturally, I was intrigued. They supported my own reaction or notion that this stuff was extremely important, and it only came to me later that you can demonstrate yourself. Or anybody could demonstrate that the water inside their cells is not liquid water. And it's so simple. You just take a razor blade, if you have guts, and cut yourself. Okay, we don't like to do that, but so what comes out? Well, blood comes out, no doubt, but water doesn't come out. The water, if your cells were filled with liquid water, if you cut yourself, the liquid would come pouring out as though it came out of a breached water pipe. It comes out. If you've ever seen it, it pours out. And surgeons say the same thing. They cut deeply. They tell me they cut a muscle, so where no water comes out. And so it can't be liquid water. It has to be something else. And it turns out it's from our studies, it's sort of, as Gilbert Ling had suggested. By the way, he passed several years ago at age just shy of 100. It's a kind of structured water, but the structure is somewhat different. Our evidence suggests from what Gilbert is talking about. It's kind of gel-like, viscous. Think of raw egg white. That's what the water, and it sticks to solids inside the cell. That's why it doesn't come out. Anyway, that's how we got started. We had some money in the laboratory that was destined to be used to study muscle contraction. I cheated a bit. I used the money to start studies on muscle contraction. But before that, I wrote a book, and the book is called Cells, Gels, and the Engines of Life. And the reason I wrote the book is to make Gilbert Ling's ideas palatable, or not the wrong word, but palatable is part of it because Gilbert Ling's writings were pretty obscure. You have to scratch your head at every page or two to figure out what the guy's really trying to say. I mean, it's deep, heavy stuff. Gilbert would sit down at the typewriter or the word processor, bat something out, send it to the publisher. That's it. The word editing was, I think, maybe the word doesn't exist in the Chinese language or something. I'm not sure, but
yeah, I understand the dynamics because I read through a lot of research papers, and they are, I think, for the most part, edited, but they are also in some fairly deep and also tangent scientific fields, and every lay person is not reading these things.
Well, I see your point, and let me tell you that even scientists have trouble reading what other scientists read. It's not just lay people. There's no serious effort to make things clear. In fact, some scientists revel in the complexity of what they're doing. They'll stand up at the podium and present something, and the hidden message is, "Hey, this is complicated. Look how smart I am because I can understand it. You may not be able to understand it, but I can understand it. Therefore, I'm really clever." That's the message.
Yeah, it goes into language to some degree. I mean, you talked before the call that I'm studying Russian right now, and it's a completely different language. The grammar's totally different. Of course, all the different words and pronunciation, all this stuff, but there's also like language subsets within English. And like you can create or repurpose a word and give it your own definition. But is it a definition that's easily understood and just kind of picked up by others? And that's important. So when it comes to structured water, you mentioned how water molecules are dipoles, that they have because of their bent and because they have a separation of electrons within their structure. They have a very minute positive charge on one side, a very minute negative charge on others. So it's basically just like a bar magnet, but at the molecular scale, atomic scale. And so that is what allows these structured properties in some ways to take place, because of the fact that if now you have a magnetic field in play, they're going to, like, order is going to precipitate out of chaos. And so there's like one definition of structured water, then maybe someone else has a different definition of structured water, and some third scientist has a third definition, and it's all the same English. So we're not even talking about different languages here. We're not talking about Russian or French or whatever. But could you, let's say, what's your definition of structured water? Like, what's a very clear, succinct, basic definition of structured water that you can provide us to help hopefully dispel some of this?
So, it's structured water is a term that is vague. The idea is that the water molecules are in some way structured, like the bricks forming a building, that sort of thing. But we found, maybe fortunately or unfortunately, that Gilbert Ling's idea was not correct. And the way we found out is that we used an electrode, parenthetically one that was designed by the same Gilbert Ling. It's a microelectrode that's used widely by biologists and that has been used to garner Nobel Prizes for various people, but not for the originator of it. At any rate, we stuck one of these electrodes into a zone of water structure, and we found it's not neutral. Water molecules are neutral, but it's not neutral. We found that it was negatively charged. And so something is wrong, because according to the idea of Gilbert Ling, the kind of structure that he was talking about, it's got to be neutral, because, you can stack water molecules which is neutral. I could do it from here to Kiev, and I would never get negative charge. So unfortunately, or fortunately, whatever you have to look, whatever you like to consider it, the theory by Gilbert Ling, though attractive, and for years I thought, well, this must be correct. We found it's not correct, and so I can go on and tell you what we found. But your question is not that exactly. Your question is, what's the definition of structure? So I guess I would define it as the way I did a moment ago, where molecules are lined up in some way, but not the way Gilbert Ling suggested, although I had hoped that his view, which was elaborated in my book to make it palatable for people so they could understand it, unfortunately is not correct. Does that suffice for an answer?
Yeah, no, well, so it's so there's some observable order within the water. It's not complete chaos. And then there's also, based on your work with exclusion zone water, how it forms these different zones, then there's also a charge separation. Would those be kind of like the two big pillars that currently, with our understanding, make up structured water? That there's first an observable order, and then there's also a charge separation that is either creating that order or is a byproduct of that order.
Well, I think it's a byproduct of the order, but yes, you're right on. So the word structure, it's kind of generic, right?
Yeah.
everything has some kind of structure, and the idea is that the water inside the cell is more organized in some way than ordinary liquid water. That's perhaps the simplest sum of it. And so it's because it's a vague term, it's maybe not so useful except for lay people as a kind of generic term. But we know a lot more about the structure now. And so of course, I think our results are, I think, valid, and many of our results are confirmed by other laboratories. And so I think the structure, and yeah, and you hit upon a really, really important aspect about the charge separation, because there's several reasons. First of all, if you start with water, liquid water gets converted to structured water, or we say exclusion zone or EZ water. It's easy to remember because this water has properties that are different from any of the known three phases of water. So we've given it a few monikers, and but when it's built, everything starts with liquid water, and when liquid water comes near certain kinds of surfaces, so-called hydrophilic surfaces, water-loving surfaces, of which most surfaces are to some extent.
Like glass. This would be one of them, yeah?
Yeah, glass that's particularly clean, yeah.
Okay.
Sometimes there are fumes that occur that build on glass, and so what was hydrophilic becomes hydrophobic to some extent. Usually it's not one or the other, it's somewhere in between. Anyway, surfaces in general, that not everyone, that are surfaces that are generally hydrophilic, when water meets those surfaces, the water converts into fourth phase or easy water. But think about the charges, because as I said, the easy water is negatively charged, but you're starting with something that's neutral. So if that something neutral is creating negative charge, it's got to create positive charge somewhere else, because you can't get something for nothing. So somehow the water is, you might say, it's splitting into negative and positive. And we found that indeed this zone, this exclusion zone that sits next to the hydrophilic surface, after the water meets that surface, it builds in sheets, and it's negatively charged, and the positive charge gets actually kicked off and sits beyond this region of negative charge. You got negative charge and positive charge next to it. It's a battery.
And so this negative charge is that an accumulation of electrons?
Well, you might say so, because if you think about the water molecule, what is it? It's protons and electrons, basically organized in a certain way. And if you have negative charge, you have preponderance of electrons creating it. And as I said, what happens is as this easy water forms, it kicks off protons, positive charges, and so those charges that are sitting beyond the EZ or exclusion zone, they're basically protons, and they're not solo protons, because what happens is when a proton finds a water molecule, of which there are quite a few there, it latches on. It latches on because we know the water molecule is a dipole. It's got plus one end, minus at the other end. So that proton looks for that minus and sticks on. And so you get a so-called hydronium ion, which is basically a positively charged water molecule. So you've got negative charge EZ sitting next to positively charged water molecules, you might say. And if you were thinking, which I know you are, you'd ask the question, well, wait a second, what keeps those apart? Because, it's like a plus and minus are like male and female. They want to get together. And so, we've learned in school, in middle school, that plus and minus attract each other. And the reason that they don't recombine is that the EZ has a structure, a very tightly organized structure that doesn't allow these hydronium ions or positively charged water molecules to get in. They're too big, too bulky. So they want to come in, but they can't come in. So you got negative and positive, and they're separated. So what does that mean? It means you've got a battery that's capable of delivering energy. And that's a crucial, fundamental, central point. Energy, you've got energy. But please interrupt if you want, because otherwise I
Well, just the battery aspect is interesting because I think most people conventionally think of a battery as being fairly large. Car battery, maybe one of these power walls, whatever, cell phone battery, it's a big thing. But the idea of, okay, how is metabolism driven? How are some of these like reactions, or, all the reactions taking place in the body, which we can't even count, they're uncountable. How are they being fueled? And water, considering the fact that it makes up so much of our molecular count, I think you said 99% of our molecules are water, which is actually, I should meditate on that really. But that effectively provides this like blanket of batteries, you could say, various scales, going all the way from down to, I guess, very small exclusion zones that exist. I don't know what the smallest ones that you've observed are. But then also, like, for example, I've done some research into collagen and connective tissues and fascia, which I find very interesting because they have these piezoelectric properties. You apply mechanical stress, they emit an electrical charge. And collagen is wrapped, like a single collagen protein fibril, whatever you want to call it, is wrapped like, so they say, like 3 different layers of water molecules. It's very, very hydrated. So perhaps it's the water that's holding on to this electrical charge. And with quantum dynamic theory of water, and the fact that it seems that water is able to form these coherency domains and capture photons and hold on to photons, which is your energy source. But is it photons that's also like driving the ordering and the structuring of this water?
exactly
Okay.
what we found. And it was a student, a young undergraduate student in the lab who was doing what he wasn't supposed to do, which I
Okay.
encourage. And he's sitting or standing actually at his bench, and he's got a little chamber, and he's playing around with exclusion zones next to. I think it was a polymer, probably Nafion. We use that polymer quite a lot as the hydrophilic surface, and many other surfaces. But he had a lamp, a gooseneck lamp sitting beside him, and he took the gooseneck lamp and he shined it on the chamber, and he saw something astonishing, and he called me in. He said, "Hey, please take a look at this." And I looked and I was astonished. And what he saw was that the region of the chamber that was illuminated, the exclusion zone or fourth phase region, had grown like by a factor of 3 or so.
Oh, wow.
Yeah, and so you know, we were actually looking for the energy source that drives the formation of this battery, because you can't get something for nothing. You need to charge the battery, and it looked as though he'd found it. So I said, "Well, turn off the lamp or take it away and see what happens." And sure enough, when he took it away from the chamber, the exclusion zone, the region that had expanded, came back to its original, so it was reversible. So we quickly started to do serious experiments to find out which wavelengths of light are the most important in feeding this or building this battery, and we found it was infrared light. We looked at ultraviolet light. We looked at the entire spectrum of visible light. We looked at infrared light, and those, except for infrared light, the others had virtually no effect. But the infrared light was really powerful. We found that even weak infrared sources, like from an LED, could powerfully expand the exclusion zone or build easy water. We could expand it like a factor of 10 even in some experiments. So yeah, photons, light is the source, just as it is in photosynthesis. And in photosynthesis, step one is you shine light, and water molecules are said to split into positive and negative components. And that step, the first step of photosynthesis, is said to be 100% efficient. And that's roughly what we've been looking at. Water molecules, by virtue of light, water molecules split into negative and positive components, creating energy in the same way that creates energy in plants. So there's a lot of similarity, I guess, what occurs clearly in nature to what we found, which gives us some confidence. So the
Plants
energy,
are
yeah, go ahead. Sorry.
plants are definitely onto something, that's for sure. I mean,
I
there's a
think
lot
so.
of there's a lot of us, but there's a lot more of them. What makes me what I think about with the infrared is that there's of course different not orbital levels, different standing waves that these electrons form. And I guess I'm just thinking of the viewer right now. We were talking about protons and electrons and water and dipoles and magnets, and some people's heads might be spinning because we're building this structure ourselves. And if you don't have all the definitions for all of them, it can be a little difficult. But effectively, all these different quantum particles and such. But with the electrons, they have these standing waves, and I guess infrared light would be the wavelength of light, or the wavelengths in that part of the spectrum, that allow those electrons to jump up to a higher energy state. And as a result, then they can peel off of the water molecule, and that creates that split. Would you say that's accurate?
No.
So please explain.
Well, okay. So where to start? I guess I can say that I have a book coming out pretty soon about the structure of the atom, and I think that what we've learned is not correct. So
I have the conventional model in my head based on.
Yeah, we all have the conventional model, but okay. Let me take a moment to talk about the conventional model. So conventional model, you've got a nucleus, and you've got electrons or electron clouds that are surrounding the nucleus. So you think about the nucleus as we understand it, and now as we're taught in middle school. The nucleus contains protons and contains neutrons, basically. And neutrons are neutral, okay. Protons are positive. Now all those protons are stuck together. They're all positive. What happens when you squeeze together a lot of positive charges? They want to repel each other. So in theory, the nucleus should explode. Now, the physicists understood that this was an issue, and 70, 80 years ago, they invented something called the strong force. And the strong force is something that is a theoretical notion. Nobody has ever, to my knowledge, found any evidence, any independent evidence for a strong force. But the strong force is postulated as a kind of band-aid to hold the nucleus together, because otherwise it would explode. So it
hasn't been observed.
No, nobody. I've never seen any.
I thought it's been observed.
A strong force, but there's more. Electrons, they're circling the nucleus, or electron clouds, as we now think. Now, I learned in middle school that positive and negative charges attract one another. The question is, wait a second, how come those negative electrons don't collapse onto the nucleus? Please give me an answer. You have no
also
answer.
Makes me think about a magnet that has a positive and negative. Why doesn't it just somehow
it doesn't
combine in and of itself?
Have a positive and negative, although I think you're actually onto something. I mean, it has North Pole and South Pole.
Yeah.
We don't think it's not necessarily, but that's another issue which maybe another time we can get into, because nobody really understands magnets.
Yeah,
So,
that's absolutely true.
yeah. Okay. So what I'm getting to is, when we talk about electrons going from one energy level to the other, that was one of the bases of the formulation of quantum mechanics. And and the issue of quantum mechanics, you have to ask a question. Quantum mechanics is something we all like to talk about because it sounds sophisticated. Quantum this, quantum that, but when you think about it, it's abstract mathematics. There is nothing intuitive about that, or as came later, quantum electrodynamics. And you have to ask the question: does Mother Nature work um, simply, or does it work based on abstract mathematics? It's a philosophical question, and I've spent all my career trying to think about simple mechanisms. Sometimes we read and we learn about complicated mechanisms, and we have to scratch our heads because we can't quite understand them. They're too complicated, and we sort of give up and we say, oh, we leave it to the experts. And I think that's happened in the field of quantum mechanics and then Feynman's quantum electrodynamics. We say, we can't get it, so leave it to the experts. They're smart, they know what they're doing. And I wonder, is that really appropriate in nature? Maybe it is, and most people would argue, yes, it is, and I'm not sure that I buy that. So it's, you might say, a philosophical consideration. I think Mother Nature works on principles of simplicity. And the book, I tell you a little story. One of my favorite students comes from physics, and he kept telling me, you got to read this book by Richard Feynman, the great physicist. People call him the Einstein of the second half of the last century, and he was popular and he was funny and he won a Nobel Prize and all that stuff. And even now, his lectures, which are in print, are very popular and read by almost every graduate student. So he said, you got to read his book. It's called QED, Quantum Electrodynamics. And finally I succumbed. I said, okay, I'm going to read it. So I opened, it's a thin book, and I start opening the book, and I read, at first there was a foreword written by, I guess, one of his colleagues. And I forget the guy's name. And the foreword says, I was shocked. He says, you won't understand this book. And I said, wait a second. This is a friend of Feynman who's written the book. He said, you won't understand it, but you should read it because it's very important. And I'm thinking, scratching my head, that's why I lost a lot of hair. I'm thinking, what's going on here? This guy is telling me I should read the book, although I won't be able to understand it. So then I thought, okay, I'm going to be rescued. I'm going to read Feynman's preface to the book, and he's going to rescue me. But he doesn't. He says, you won't understand this book. He said, how do I know that you won't understand it? Well, he says, none of my students understand it. And in fact, I don't even understand it. And I originated it. So I try. I get through about 10 pages, and I simply can't get it. And the reason you can't get it, or some people get it, I guess, but I can't get it because it's an abstract notion. It's not based on intuition as most of science is. Hypotheses and such. It's abstract mathematics. So you introduced the topic, and I apologize for my failure to buy into the question that you're asking. But if I'm honest, I've got to say that I have some questions about it myself. I'm entirely unsure about the applicability of anything that starts with the adjective quantum. We all use it. It sounds sophisticated, but not many of us really understand it. So maybe, please.
What does seem to resonate with me is this concept of waves and how things exist as waves. And so, like photons aggregate into waves, which then aggregate into fields. Um, they say electrons form standing waves. Of course, we see waves in water. So the idea of waves, and if let's say an electron does have a particle and it does, actually you can observe it as specific point in space-time, um, how they're actually situated together with all these other particles. Like I like to think about the parallels that we can draw with like society and how people are in their places and different things and how everyone's moving around, but you might never see this person there or that person in this spot because that person has no interest in ever reading books and going to the library. And I think the universe mirrors itself all the way from the different scales going up. And I find that I agree with your idea that on the whole, that there is a beautiful simplicity to things. I do think there's also crazy details if you dig into it. But it does seem that the most wondrous things in nature typically have the simplest science and math behind them. I mean, like Romanesque cauliflower and like the golden ratio, Fibonacci spirals and everything. It's a very, very simple equation. And I did some, before I got into YouTube, I was a geophysicist, and I did a research project during the COVID lockdown with a whole bunch of seismic gear because less people were driving, and it created a lot less artificial noise. And we were looking specifically at microtremors. So seismic microtremors, these microwaves. You can do Fourier transforms on them to pull out the different spectra and everything. I had an idea that of the different surveyed geometries, like how does the actual arrangement of the seismometers influence how we collect the data, how we see it? And the standard arrays that my mentor used were triangles. Then also, I mean, you could do a square, but typically it was triangles, lines, L's, sometimes circles. And so we found a perfect day. We had a huge yard, field. We had a huge field, and it is very good wind throughout the day, which creates these surface waves. And there's these big trees, these big redwood trees in Napa, California. If you've ever been to Napa, that's where I grew up. And so these big redwood trees were collecting all this wave energy from the wind and creating these nice surface waves as our energy source, you could say. And so we did all the different survey geometries using a good amount of seismometers, but then we also set up a Fibonacci spiral. And I've been experimenting with this, but I hadn't done comparisons on the same day, same location, same processing techniques. And the data for the Fibonacci spiral came back quite a bit better than the others. One of the reasons why is that because of the unique arrangement of each geophone to the others was collecting these sound waves, it created a lot more combinations. And then there was also, multiple pairs of the same number. Let's say going from 5 to 8 was 3, but there was also a distance of 3 at the beginning. So you get overlap, therefore you get, more better averaging. But the Fibonacci spiral pulled out the best data by far. It was like the others, they looked nice. You could present in a report, your client would be happy. But the other one, honestly, it looked like art. And I actually printed that out, and it's in my mom's house hanging on the wall because it's just this beautiful, beautiful seismic curve. And it shows the shear wave velocities. And I wasn't surprised that the Fibonacci spiral survey geometry was the best. And it's almost like the data wanted to be collected in that method. I know it sounds a little silly, but it's just such a better method of observation because of how you get all these different connections and a higher density of different wavelengths that you're measuring. As a result, you can do better statistical analysis computation for you or whatever. So I feel like the way we measure these things is also very important, and sticking to those simple principles in how we measure things is important. Um, but yeah, the truth resonates. It's interesting that you mentioned Feynman in his book Quantum Electrodynamics and being so difficult, or even him saying that he didn't understand it, because with like the lectures that you watch, generally he's pretty good at explaining things in a very simple, forward way. He has wonderful metaphors that he uses at times to explain things like electromagnetic waves and such. So for him to kind of have his polar opposite, where I don't even understand what I'm writing, seems a little bizarre. But I haven't
Well,
tried reading the book yet.
he's very, very popular. I don't know if you've read the book, his wonderful book, Surely You're Joking, Mr. Feynman.
Hmm,
It's
I've heard of it. I
everybody.
haven't read it.
Oh yeah, it's so funny. He talks about um, being at Los Alamos, and it was a very secure place, and it was supposed to be a secure place, and he was able to get out underneath the fence, and then he'd walk in, and in the main gate, and they said, "Well, you can't come in, Dr. Feynman, because you didn't leave. So how could you come?" And he was an expert at safe cracking, and he was funny.
Yeah,
And I've heard stories about him at Caltech. So the president or the provost was having great difficulty getting the faculty to come to important meetings at the university. So he said every Tuesday at 11 o'clock, there'll be no classes. So everybody, all the faculty members were free and they could come to the important meetings. So he decided to set up lectures exactly at that time. And then, all the people would come to his lectures instead of going to listen to the president of the university talking about academic affairs and such, because he was so interesting and so charming and so funny. And I know that graduate students in physics almost uniformly read his lectures, and I've read a few of them myself, and they're really clear. So he had, I think, one of the reasons for his popularity was indeed his charm and his intelligence
mm,
and his ability to see things. On the other hand, I still have the same comment about his major achievement. He was good at mathematics, and he came up with this theory. It won him a Nobel Prize. Sometimes I wonder whether some areas in science, whether the achievement rests at least in part on the charm uh, of the person who comes forth with the idea. Um, you know,
absolutely.
their brilliance and charm. Their colleagues appreciate that, and the appreciation is the first step toward recognition. Um, which leads to Nobel prizes and stuff like that. It's just a speculation on my part. But
Well, I
anyway,
mean,
we're just. I'm sorry. Go ahead.
well, you can look at Einstein and how he got a Nobel Prize for his 1905 paper, but not for his his general theory of relativity. And they were like, "Well, we had to give the guy a prize," but there was all these. Some people didn't like him because of the politics at the time, right? It was getting really charged in Germany and Europe in general. His stance with World War One, so that all influenced it. And that was back then. It's probably way more political now. Of course, how often do you see behind the curtain? But a contemporary of Feynman was David Bohm. Have you ever heard of David Bohm and some of his
Yeah.
theories? Are you
Well,
well?
yeah, a little bit, and I've listened to him, and yeah, but I'm by no means expert on that.
He really lays out a different kind of theory for how you could say the universe works in some ways with his book uh, Science, Order, and Creativity. And I really liked how it did talk about all three because they are separate, but they're connected. And so he has different theories, implicate order, super implicate order, about how things are manifesting into existence and then like leaving existence, and this is a different way of understanding the universe, and that's not all based upon the prior quantum foundation. Um, and it it felt very I mean, every thought is an abstraction. That's a quote of his. So any idea, any thought is not actually summarizing the truth. But that definitely rang true in many ways. And that was a very influential book that I read, I guess a year ago, my last time I was traveling through Europe. And so I would really like to see more people read that book, or at least just be exposed to Bohm, um, because yeah, he may not have had the charm that Feynman had, and uh, and also because once certain energies build up, it's like, okay, well, we're going to dismiss everything that this person does because it doesn't fit within an established model. Then these things like resentment can build up and such, and that then influences how the work is perceived by others, and it gets very, very complicated because we're human. But I thought his book is very, very carefully laid out, and also anyone can read it. Um, and so, yeah, I wanted to see if you were aware of that. But what strikes me is the kind of the similarity between you and Bohm and some of these other scientists throughout the ages in terms of kind of being like a natural philosopher, and how it's more looking and observing what is and then building the framework from that, rather than um, you know creating these crazy mathematical models that, okay, well, maybe we can observe it in 100 years. Um, because like Da Vinci, for example, was actually, looking at these things just as a kid. He was just making a lot of observations, and then he came into his scientific brilliance. And so, with your lab, has it really just been, okay? We're going to set up a bunch of different experiments, very simple experiments, then some more complex ones, and just make the observations and find what fits everything together. Is that how you're operating with your
That's
lab?
exactly how we operate. I don't trust complicated experiments because there are lots of things can go wrong, and we all have our hypotheses and favorite ideas, and sometimes if you have a complicated experiment, it's kind of easy to shape the outcome to fit what you would like the outcome to be.
Mm,
We all have that kind of bias, but when you deal with simple experiments, like the ones I like the best, that you just look in the microscope and you see something moving from position A to position B, and there's not much doubt that that thing has moved from position A to position B. You can see it with your own eyes. There are not too many alternative ways to interpret that, except it's moved from A to B. It's those kinds of experiments that for me are the most compelling, the simple ones, and also simple logic. Um, um, if you go through a logical sequence, and it's very easy for anybody to say, oh, he made a mistake here. His logic is, what I'm getting at is that if you base your ideas on simple experiments and simple logic, they're transparent. It's all transparent, and anybody who thinks that there's something wrong can easily spot it. When you're dealing with something that's very complicated and dealing with complicated black box experiments where
mm,
there's a lot that goes on in that black box between the input and the output, and it's hard for all of us to really know for sure what's involved. Then it becomes more difficult. So is what I've learned in the years of doing science, that let your ideas um, rest on simple experiments and logic. Then you're treading on um, stable terrain, I think, and it really yields. Um, uh, it works. It seems to work, and that, I think, is what science has always been about. You have an observation, you need to explain it, um, and use simple explanation, simple logic. You're familiar, I know, with Occam's razor principle.
yeah.
So yeah, and so it was. it was Sir William of Ockham, um, a theologian from, I don't know, almost 1,000 years ago. You know, and he was interested in the question: does God exist, or does God not exist? You know, and he said, famously, he said, well, there are two hypotheses. One is God exists, the other is God doesn't exist. And the simplest hypothesis is the one that probably will lead to truth. And then a few hundred years later, Newton thought, this is a cool idea. And he said, the same idea should apply in science: simplicity. You know, the simplest hypothesis is the one that's likely to be valid. And scientists for hundreds of years rested on that premise that you got it. The simplest one is likely to be the correct one. All of that changed 100 years ago with the physicist and abstract mathematics and such. And as Einstein famously said, God doesn't throw dice,
Yeah.
something like that. So anyway, I see my colleagues sometimes standing up in front of the audience, presenting something of huge complexity, and the implicit message is, oh, you guys, you don't really need to understand it, but I understand it. And therefore, look how smart I am, because I'm capable of understanding this stuff that may be beyond you. But I'm significant because I can understand it. And well, um, I think I'll stop there on that theme.
One of the things that is really important to me is looking at things holistically. Before I got into before I went to school, and then before I got into really diving into a lot of this science and conducting like the geophysics that I did, and then also just diving into a lot of this research and all the different ideas, is I've always been in health and wellness. So there's a big aspect of health and wellness with my channel and my website and things of this nature. And I think the holistic view is very, very important. And taking these different fields and connecting them together as best as possible, trying to find how they connect and how there's a larger kind of simple message that they present. Um, and so, yeah, I don't think it can always apply, especially if you start to like look into nitty gritty details. But science is definitely dissected, like modern science is just like a constant dissection and splitting and splitting and splitting. And we've gotten really good at analyzing, like you can look at like, the spectrum of light of here's this exact wavelength, and here's this exact wavelength. But it seems that there's fewer people that are looking at light as a whole and looking at that concept. And I think that's really important for us to look at things as a whole. So when it comes to water, and it has these these structure properties, this charge separation, clearly it's very, very electromagnetic. And our entire existence seems to be kind of based on photons. At least the more I've dived into it, it's been the deepest rabbit hole that I've found. What's your understanding of photons, or maybe this is incorporated with your new book? Like, can you talk a little bit about that, how it interacts with light, or how it interacts with water, and how it interacts with our body? I mean, you've also done all this work into muscle contraction, which is interesting. And so, I don't know, maybe do you have like a holistic map in your mind that you could share with us?
Yeah, I think I guess I do, and I've come to appreciate that the world is electric in nature, and uh, and that photons, uh, well, back up a step. Basically, electrons and protons are consequential for just about everything that exists in nature, and so my next book deals with that subject, and it's going to be called Charged, and then the subtitle is the unexpectedly profound role of electricity in nature,
Mm,
and and we and the main theme of it has to do with the fact that we've basically omitted charges, electrons and protons and such from our thinking. We think about nature not in those terms pretty much at all. And I deal in the book with half dozen different aspects of nature. And the main theme is that we think we understand, but actually, if you go one step deeper, you really don't understand. You can't answer. So, take, for example, gravitation. So, we think of gravitation in simplest terms as masses attracting one another. Of course, there are more complicated interpretations that the physicists would invoke, but essentially, if you ask anybody, they say, "Oh yeah, well, yeah, the reason you're drawn to the Earth is that the Earth has a big mass and it attracts your mass." And so I think most people would say, yeah, masses attract, and there's a good deal of evidence that seems consistent with that. But if you look a little bit more deeply, you find that there are a lot of observations that don't fit. Most people don't know about them, but I list some of those in the book, and so you have to ask the question, and this is the main point. You say that masses attract, but then you go one step deeper and you say, why do masses attract? And you get a blank stare, even from physicists. Why do masses attract? So that the point is, maybe there's something else that's going on there that is one step deeper, that actually forms a coherent idea and hypothesis that makes a lot of sense. And so that is one aspect that I deal with in the book. Another one is weather. So if I ask you, can you start from first principles of physics and chemistry and tell me how you can explain the hurricane that's now approaching California? And I'm confident that you say, well, from first principles, no, I know something about low pressure and temperature, but I mean, starting from first principles of physics and going on to build an understanding of weather, of how it actually works. How does a cloud form? Why are clouds, which are built of water largely, why are they floating in the air instead of coming down all the time? So you need to be able to one needs to be able to answer questions like that from first principles, right? Because there is weather, and you ought to be able to understand it. And so,
Well, I give it a stab. The one thing that I think of is just vibration, and how things that are bound up in these structures have these lower vibrations. And then, just like if you look at the atmosphere, for example, air molecules at the surface, there's more of them. They are air, so they are vibrating faster than liquid, and they're vibrating, which vibrates faster than solid typically. And then as you move up, the charges the vibrations build until you get to the ionosphere, where they're fairly vibrational. There's some like neutral atoms there as well, but generally they have quite a bit of energy to them. And then you go into the radiation belts, which is like kilo electron volt and maybe even like mega electron volt in range, depending on if it's proton or electron. And so in many ways, it just seems like how much energy does a particle have like in it that determines where it is in kind of like this graduation out. And the lower vibrational particles clump together, then the higher vibrational particles clump together. And so with that can explain a little bit, I guess, of maybe first principles, perhaps, some of these things. But it also seems that energy, it's really interesting. Like a thunderstorm, for example, you have these lightning bolts that are just shooting out, what we think are electrons. We can measure them. They make these telluric currents in the ground, and you see the flash of light, and they create extremely low frequency waves at near 0 hertz all the way up to gamma rays at times. So there's these gamma ray flashes that a lightning bolt makes. So here you have like this slow moving like thunderstorm, yet it's emitting these photons all the time, and these photons are traveling at the speed of light. That's normally what they do. And so it's interesting that like there can be like this accumulation of these particles or these resources that normally travel at the speed of light, but here they're like brought and made slow. And I think of like energy density and how it moves across space time really interesting. It seems like I think there's a consciousness to it, but that's a controversial idea, I suppose.
Well,
But if we're conscious,
we're actually studying that in the laboratory about consciousness, but let me just return to because I believe so too. But let me return to your point. Could you take your hypothesis and go on to explain thunderstorms and hurricanes and tornadoes to a middle school student?
not right now.
That's
I would have to put some work in.
well, I think that if you got the right idea, you ought to be able to explain it to
Absolutely.
anybody, any intelligent person without necessarily a whole lot of education. You should be able to start from the very simple postulates or principles and build up from there. I'm not exactly advertising my forthcoming book, but we try, or I tried to do that in 4 chapters of the book, and I ask other, simple questions that need to be answered, like what creates the wind, and some people spout off, oh, obviously you got a low pressure next to high pressure, and you got wind, and um, you know, does that really explain it? If you got low pressure next to high pressure, how come they don't equalize instantly? What sustains that pressure difference? Or is there something else? Is there a kind of first principle that you can start with and explain the winds? What turns the earth? Why does it turn every 24 hours? You think that there ought to be a simple principles that can explain that. How do birds fly? And again, if I were to ask you how birds fly, you'd say, oh, they flap their wings. But some birds don't flap their wings, or some birds rarely flap their wings. I can see
Yeah.
from where I'm sitting right now, my home has a lovely view of lake and mountains in Seattle, and there are eagles nests nearby, and I see the eagles flying on a daily basis, and they rarely flap their wings, and they can go against the wind, with the wind, right angles to the wind. Sometimes they can fly steady. Sometimes they lose elevation. Sometimes they gain elevation. They don't flap their wings a whole lot. So something else is going on, and we need to understand again from first principles. How do they do it? How do fish swim? If you read in the book, say, well, they undulate their bodies. But wait a second, if that's a really good mechanism, how come engineers building ships don't emulate that, build ships that way? You haven't witnessed a ship or ferry or whatever that undulates its body. So something else is going on, et cetera, et cetera. The point being, you got, in my view, it's necessary to start from first principles, and you need to be able to explain these various phenomena, and that's what I try to do in with water. And we've deviated from that central theme. But my book, the latest book, The Fourth Phase of Water, it attempts to understand a lot of nature, starting with water in very simple terms, and I think, at least if you judge from the Amazon reviews, of which I'm pretty proud, I think that I've achieved something, starting with an understanding of water from first principles and from very simple and straightforward logic. And so it's taken a bit of time, but people have really taken up this stuff and started to build in many different directions. Just to circle back to some of where we started, energy is really important. And the question is, we've got this battery that we're talking about. Is this battery completely, if it exists in your body, is it completely irrelevant, or does it supply energy for us? You see, and the evidence that I bring forth in the book is that it indeed supplies energy. So like people who don't eat, for example, the breatharians, where do they
Yeah.
get their energy? you know, and et cetera, et cetera. So yeah, it all rests to a large extent on simplicity, on simple ideas. How far can you take a simple idea to explain what you see in nature? Is what
If
science is supposed to be about. Science
finding
is not.
those uh finding those really good solid foundations. Yeah. So I'm glad you're doing that. And if if we go back to the battery, I like how we've gone all over. I think it's really cool. And because I like these conversations that have take homes, but then also leave someone with a little bit of a sense of wonder, something to meditate, ponder, think about, because that can give you so many more take homes with your own kind of at home processing. Uh, but if we go back to the battery, um, now in the cell, you have the cell, the cytoplasm. It's easy water, and if I'm correct, the cell potential is determined. I think you wrote that is determined by protein balance. Is that correct?
By what did you say?
By protein balance.
Protein balance?
Yeah, like the amount of proteins in the cell. Like how do proteins in the cell interact with easy water, and how does this change the charge of
Yeah, well,
a cell, and
okay.
how does it change the battery properties?
Yeah, I mean, that's central because it's the surface of the protein that acts as a nucleating surface, the hydrophilic surface of the proteins and other solids inside the cell that build easy water. So the cell is filled, a healthy cell is filled with easy water. But the question of electrical potential and easy water, just think about it. If the cell is filled with negatively charged easy water, it's like, you have a bag filled with something that has negative charge. Of course, if you stick an electrode in the cell, you're going to measure negative charge, right? And so, um, in my view, the reason that the cells have negative electrical potential is exactly that. It's because the cell is filled with negatively charged substance, easy water. That differs completely from the accepted view that it's a cell membrane that has pumps and channels, and that somehow interact with one another to produce the cell's negative electrical potential. Almost everybody thinks that. I think it's wrong, and and there are again very simple logical principles that I think demonstrate clearly that that's wrong. There are a half dozen of them. I've written about it in various books and papers, and I think it's simply wrong. Um, if you want, I can go into some detail, but I think the answer is as simple as it gets. The cell is filled with negatively charged junk stuff, easy water, and therefore it's got negative charge. And of course, if that's correct, it has very serious implications. Um,
Hmm.
think about, well, I don't know how far you want to go into that, but
Well, I just have one question before diving into that a little further, because I do want to talk more about that because there are some further follow-ups I have for you.
okay, sure.
But you said you do a bunch of very simple experiments with your lab. There's, I mean, there has to have been some other labs and universities and independent research organizations, et cetera, that have confirmed your work. Yeah.
Yeah, yeah, yeah.
So
And the
so what's like the lag time between like you do an experiment, you publish the results, and then the normal scientific method, uh, the next step kicks in where it's like, okay, we're gonna try to replicate it, we're gonna try to replicate it, and then they do. Like, what's the normal lag time? A couple of years, 6 months? Not all of them probably have the same amount of interest in them.
it's a good question. I don't know that I have a simple answer because it's because of the system of doing science. Um, if there were not politics involved, it could be pretty quick. Um, Sometimes politics get in the way. So the example is this fourth phase or easy water. Now steps on the toes of many scientists who have come up with belief systems that differ. And indeed, there have been some papers that challenge, provide different interpretation of what we found. And a lot of people who are in science now are very sensitive to the political issues. So, for example, suppose you're let's say you're not a geological scientist, but suppose you're, say, a biological scientist, and you hear about this fourth phase water stuff, and it kind of intrigues you, and you scratch your head for a moment and think, well, I'm not really sure. I'd like to do these simple experiments to see whether this crazy guy from Seattle is correct, or not correct. And and your colleagues say, well, Stefan, hold your horses. If you start diving into this stuff, you're going to have real problems because you're going to apply for money to get a grant, and so you apply and you say, well, I want to study easy water. I want to see if this stuff is right, and I have some ideas. If it's right, I could go beyond it. And you submit your application either to the National Science Foundation or National Institutes of Health, the major funders, and they're gonna find so-called expert reviewers to look at what you've done. Now, the expert reviewer is not going to be someone who's interested in fourth phase water, because this stuff is new and revolutionary. It's going to be somebody who's involved in conventional ideas, which this fourth phase idea challenges. So, in other words, you're going to be providing or submitting a grant application to get reviewed by someone you're challenging. It's like, French revolutionaries going to Louis XVI, and we have a few gripes, and are you going to get listened to or worse? And so your career is on the line. And if your family's hamburgers, bread and butter is built on making sure you get these grants to pay your salary, you're going to be a little bit circumspect before you apply for a grant to give you the money to do the experiments that you want to do. This is a giant problem. This is an overwhelming problem with the grant system. Absolutely. And if I ask you the question, since the grant system has come into being, or let's say during the past 30 years, can you name a scientific revolution? We're all interested in scientific revolutions. Can you name a scientific revolution that's occurred that's of the same magnitude, say, as splitting the atom or defining the genetic code? And I don't mean a technological revolution, like my iPhone.
Yeah.
I mean a scientific revolution. If I ask you something that's already succeeded in changing your life in a major way, just like those two have done, can you name one?
Yeah, not really. The paradigm is still there. What that does make me think of is how, there's been a lot of buzz just over the past couple of weeks about LK99, this room temperature semiconductor. And perhaps water is our room temperature semiconductor. What are your thoughts on that?
I think it might be. Absolutely. Yeah.
And that might be that paradigm busting scientific revolution.
It might
really
be,
understand water.
But we're talking about a paradigm that has come into being, that people have accepted, and that has succeeded in changing your life in some way. So that you may be onto something. I don't know. I'd like to think that maybe what we're doing is maybe such a paradigm, new paradigm, but it remains to be seen whether it needs to be accepted, and people need to digest it, need to build on it and such, and that takes some time. But that's what science is all about, and if you pause, and if you can't name a half dozen half dozen scientific revolutions that have happened with all the massive amounts of people and money and science that occurred in the past, 2 or 3 decades. Something's wrong with the system.
They haven't
Like,
cured cancer.
well, that's another issue.
Like the amount of money, the sheer amount of money that's gone into that, and it seems like very little progress is made. But you could look at something like fasting and autophagy, and that's going back to first principles, like just don't feed the cells, like activate the body's normal cleanup system. If you want to keep it really simple, and it works. And then you add in some, you combine that with traditional methods like chemo and makes them more effective. But that's like it's like a free thing to do. It's actually like saving you money. Like don't eat, like just don't do anything, right? It's so simple.
Hasn't that been known since Ayurvedic times?
Yeah.
I'm talking about something, a new revolution. We can think back a few thousand years. The ancients were quite wise in their thinking, but we've mostly rejected their ideas in favor of, quote, modern science, unquote, which hasn't really gotten us very far. So I mean, the major point I'm trying to make is that if science is really working, we should have scientific revolutions coming one after another, and it's not happening. And we might think, well, scientists are maybe stupider than they were 100 years ago, or they don't have enough money or something, but it's not happening. And I think the reason is it boils down to what I was just talking about, that if you have you need money to do research these days, and you have to apply for money. And if you challenge the belief system of the reviewers, you're not going to get your money. It's as simple as that. We've invented something called the Institute for Venture Science. That's an organization to try to circumvent that. We're looking for ideas that challenge mainstream views, and the idea is to fund those people and to try to ensure that they really have an opportunity. It's called Institute for Venture Science, ivscience.org.
I'll put the link in the video description, everybody, so you can go check that out. Donate if you want.
Sure, yeah, and we're looking for people who believe in that, who are willing to make some donations, because governments won't support that. It has to be through private donations. And we've identified already some people who are doing some challenging work that we think are worthy of support, because they could create scientific revolutions. So yeah, sure.
Well, I asked the question going way back to confirmation of easy water by other people, because there we go. Because if you're to build this new framework from these first principles that you've discovered in the lab through simple experimentation, of course, it behooves to have multiple people all say, yeah, we saw this too. So that's good. So this battery idea of how these water batteries, if you want to use some, that language, right? How these water batteries are an integral part of like life and metabolism and like life force energy and things of this nature. What are the factors that can influence and change this battery dynamics in a positive and also in a negative health detrimental way? For example, like if you had a cell that just started to produce an overabundance of proteins, for example, and how would that change the battery dynamics? Would be good? Would be bad? When a virus comes in, all of a sudden it's just like make all these viral proteins. We know you get this health downturn, but this idea of the energy of life and how if we can understand some of these things, how we can maybe use that information and knowledge to improve our own health and vitality and wellness. I think that's very useful.
I'm not sure where to start. It's a really profound question that you're asking, and I guess I would start by saying that your cell is filled with easy water, and easy water is critical for everything. If you don't have enough easy water, your cells are not going to function. And the reason for that is that and this is revealed in my Cells, Gels, and the Engines of Life book, that when the cell operates, let's say take a muscle cell. So a muscle cell may be spending most of its time not contracting, but then it
Yeah.
contracts and then it relaxes again. Yeah, you got it. So what happens? And I provide evidence in that book that what's going on is that I use the term structured, and when I wrote that book, it was 20 years ago. The structured water undergoes a transition, a so-called phase transition, to ordinary water. And it's that transition that's responsible for precipitating all the action of the muscle cell. And then when the muscles finish contracting, then the cell reverts back to its original condition where the water is structured, ordered, and the proteins are back in their extended instead of contracted configuration. So this phase transition occurs in many different kinds of cells, and the cell action is a result of this phase transition. Now, if you don't have enough easy water, it can't undergo this transition, and so your cells are dysfunctional. So you must have a good complement of easy water. And we don't have enough easy water. The cells are either dysfunctional or pathological. So if they're dysfunctional, what you want to do is rebuild easy water in your cells. And I've been talking about a half dozen different expedients that you can use to rebuild your easy water. And some of them are pretty simple, like drink more water is one, because the water that you drink, some of it gets converted into water and you get the buildup that you need. Another way is to drink easy water. Now, the way you can do that is to take the plants in your backyard, so-called juicing. You take the leaves and you squash them and squeeze out the juice. And what is the juice? The juice is the water from inside the plant cells. And they're full of easy water, just like our cells, when they're healthy, should be full of easy water. So you get the easy water directly. That's another way.
And a lot of hydrophilic surfaces, yeah?
Well,
Like
yeah,
the cell membranes and stuff, the cell walls.
Sure, the plant, yeah, right, absolutely. So that is one way, and there are other ways, like for example, sauna, or as the Finns say, sauna. And what does that do? Well, it provides, you're surrounded by heat, which is essentially the same, not identical, but for all intents and purposes, infrared energy. Infrared energy builds easy water. So you go into the sauna, you feel tired, depressed, muscle aches, and you come out after 20 minutes feeling a lot better. Why is that? Well, I think one reason is that it builds easy water, because in the lab we know that infrared energy builds easy water. And so you return to health, et cetera, et cetera. And I just want to, before we run out of time, go to the issue of cancer. You raise the issue of cancer. And you raise the issue of, people have been studying cancer now for intensively for 50 years. It was our President Nixon who declared war on cancer. That was more than 50 years ago, and the war has not been won. At least, many would agree that the war has not been won. And what's going on here? So the general opinion, I'm going to get back to easy water in a moment. The general opinion is it's too complicated. Scientists have been studying this problem now for 50 years, and because scientists have not found the answer, the conclusion is it's just too complicated, right? And that's one possible answer. The other possible answer is you're not looking in the right place. It's like the guy who lost his keys to his car, and the policeman comes over and says, "Well, can I help you? I lost the keys to my car." And the guy's looking right near his car. Is this where you lost the keys? No, but there's a lamp just above, and I can see.
Yeah.
So, but it's not where the keys are, and so maybe the keys are somewhere else. Well, I think they are. And
the lamppost is the funding saying, "Hey, look here."
Yeah, exactly. And the funding is, so if you have an idea that has to do with genomics, apply for money and you'll get a few $1 million if you have a decent proposal, and you'll go on studying genomics. But if the answer does not lie in genomics, but maybe it lies in something like easy water, you'd never find it, right? Well, I think it does, because um, uh, it indeed may lie with easy water. As I said, if you don't have enough, there are 2 points that I've already mentioned. Number one, if you don't have enough easy water, your cells are not functioning. Number two, the cell's electrical potential is a consequence of easy water. You have a
Yeah.
full complement. Okay, well, normal cells, like your cells are very healthy. Mine are less healthy, but yours are very healthy.
I
And
hope
if
we're
I
both healthy.
Well, sometimes I, I think mine are, but uh, typical electrical potential is minus 50 to minus 100 millivolts. And
Mhm.
early in my career, I used to study this. I used to stick electrodes into cells and measure that. And you knew if the cell is minus 70 millivolts, you got a healthy cell. And if it's minus 10 or 20 or 30, then throw the cell out and begin your experiment again with a
Mm.
healthy cell. Well, cancer cells, it turned out, this is the key. Your healthy cells are minus 50 to minus 100. Cancer cells are minus 10 to minus 15.
Mm.
They don't have very much easy water. They're basically non-functional, or reduced function. And also, um, it's been shown like 50 years ago. What is the cancer cells divide all the time? They just keep dividing. In normal cells, what is the condition for allowing cells to divide? Well, it was found like 50 years ago that when the cell potential goes from minus 50 to minus 100 down to close to zero, um, that's a signal. It stays there. It's a signal for the cell to begin dividing. It has to stay at that.
Mm.
But cancer cells are there all the time. Therefore, cancer
Of
cells
course.
keep dividing. So,
Well, this is interesting because it touches on a few things. It touches on like cancer cells are multinucleated at times. They have a whole bunch of this DNA floating around, all this stuff that would influence easy water properties based on your work, because they're more positively charged. But also the idea that these charge separations and the cells individually then collectively form these larger cellular voltage gradients. There's great supportive work in the field of morphogenetics from many, many years back that I'm sure you're probably aware of to some degree, showing how these cellular voltage gradients influence genomic expression. So it's interesting that the main push into the field of cancer and trying to solve that is looking at genomics. And they're in some ways right, but what is driving gene expression in many ways, based on some really, really good research from, for example, Robert Becker, then Michael Levin, who's doing some really interesting stuff now, um, is driven by these cellular voltage gradients, which would be primarily, it seems, as a result of water and their dipole structure, because 99 out of every 100 molecules is water. So 99 out of 100 are these little magnets. And uh, yeah, so then how like, what are the electromagnetic, like are you familiar with the term like interference pattern?
yeah,
Yeah, so like what's your interference pattern? And like how does that influence your health and wellness? So how's that like how does this influence pattern that's always changing but also has some structure to it? How does that just then manifest itself as like who you are as a person? And I find that really interesting and leads to way too many questions that I would like to explore all of them. But
well,
I,
that's too complicated for me.
we
You
certainly
know,
don't have enough time, but just to provide like food for thought for people, just how some of these basic things. This is what I really love about combining health and wellness practices and science, and also kind of like looking a little bit beyond to the next like hill or mountain, is because it's like here's some simple principles here's some very interesting science as to how this has very big ramifications, whether it's for health or whatever. And then here's like what that may lead to, and how perhaps by focusing and like optimizing this, you can then also change that, which there isn't much perhaps evidence for yet, because it's that's beyond the current paradigm. As a result, people for sure most people outright dismiss that, because it's not even like you've done science, you've had people replicate your work. So yeah, I mean, maybe it's controversial, but there's also, you do have supporters. Like, it's not like I'm doing a podcast with someone else. I'm doing a podcast with you. You do have a support system. It's good. But there's certain things that are so far from the paradigm, they're just totally dismissed by most people. But that's why I like focusing on these base concepts, because sometimes they provide, it seems, evidence here, or at least this provide for idea germination.
Yeah.
But yeah, if you have more time to expand on the on kind of like the life force energy aspect of water, I think that'd be great. But if you don't have the time, then I totally understand.
Well, maybe last point, because I do need to go, and that is when you say a life force and such, there is something beyond what we sort of have come to understand, and that is the idea of information, subtle kinds of information that occur. And those of us who are grounded in the physical sciences, as I am, like to think that that there isn't really such a thing, but I think there is. And I organize each year the annual conference on the physics, chemistry, and biology and we get people who come and present evidence that there's information in water. And this is not only people like Masaru Emoto, who many people know about, who pray to water or send energy to water and look at the crystals, and gives you beautiful crystals, and negative energy gives you ugly crystals. But I'm also talking, and he was a spiritualist, but I'm also talking about scientists like, for example, the late Luc Montagnier, who won the Nobel. Yeah, I mean, he came to our conference every year and presented his evidence on information in water. And
I have the note here to talk about that. We just didn't have the time, so I'm glad that you brought it up.
I just want to say that his primary evidence is now confirmed by published by 3 different groups, 2 Italian and 1 Chinese. And so, if we take confirmations by other groups as evidence for the reality of it, then it looks like it's real. And in what he found is remarkable. He would put some DNA in water or in a buffer, and it's a short strand of DNA, maybe 100 base pairs, and he might dilute it and almost homeopathically, or he might not. And this is a completely sealed vial; nothing can get out. And nearby is another vial filled with water. And his hypothesis is that information from the DNA, the sequence of DNA, is being somehow imparted to the water that's nearby. And then he takes the water to test his hypothesis, and he uses the PCR technique, which people know about because of COVID, the PCR technique to amplify DNA, and the structure of the DNA that he gets is the same as the original that the water had been sitting next to. Unbelievable.
The base water that had nothing in it, put in all the base pairs and put in the was it protease enzyme? Whatever the enzyme is.
You need for the eventually for the PCR reaction. I'm not an expert in it, but all the stuff that that you need. So usually, you would usually insert a very small amount of DNA, and you get an amplification of the DNA. So, but all he's doing is putting in water now, and and the water is said to have the information because it was sitting nearby DNA or nearby the water that surrounded the DNA. Okay, so main point is that there's evidence now from spiritualists as well as scientists, as well as distinguished scientists, the full gamut, and demonstrating multiple ways that information is actually stored in water. And we've begun studying this ourselves, having healers coming to the lab and sitting beside water and seeing if there's any change in the physical chemical properties of the water before and after. We have no data yet. We've just started those experiments, but
Cool.
it's very important. And nobody understands how this happens or how it can happen. This is, and that's what science is all about. If you have an observation that can be repeated and such, it's our obligation to figure out what's going on. It's not our obligation to dismiss it and say, "Oh, it's impossible. It just can't happen because there's no known mechanism for it." It's our job to find out what is the mechanism. And admittedly, the mechanism for this is unknown. And so it's up to us. So maybe that's ending on a positive note or a negative note. I'm not sure how you would consider
Yeah,
it.
some ability for water to capture. Well, Luke thought it was electromagnetic waves and photons that then were captured, and then some amount of them were able to then split over into the other one, and they contain the information of that DNA assemblage. And then 100 base pairs is quite. You can't just fake that. It doesn't happen randomly. That's definitely a cause and effect, that A to B that you talked about. So just everybody, there's a lot of different threads here that we could have gone down. I hope that you see some of these different kind of paths and things to research into of your own. I apologize that we couldn't get into all of that because that would have been a very, very, very long podcast. But I just have one final simple question for you, because I think this is always very interesting, that sometimes you have scientists who are looking at some of these very base fundamentals or making some of these remarkable observations. I mean, we just finished on how water can contain energy information. I have a couple of videos on that and some of the potential science explaining it. And then you talked about bringing healers into your lab, and you're just starting those experiments. And what I always like to think of is for these scientists that are making these observations, how has that changed and impacted your life and your maybe some of the health and wellness practices that you have? What are some things that you've learned through the lab that impacted your lifestyle in a direct way? I do this now. Absolutely. Are you juicing every day, for example? I just find that very interesting. How does it stay abstract or?
That's a really good question, and I feel myself slightly embarrassed because I don't take good care of my health. See, if I knew that this interview was coming, and what I should have done, instead of putting a cup of coffee next to me, I should have put a glass of water next to me because I know the importance of
I got the water.
Well, you're smarter than I am. I've enjoyed pretty good health most of my life. Lately, there have been a few issues, and I know what I should be doing, but frankly, I mean, I shouldn't be sitting right here without moving my legs and such and exercising, but I tend to do that, and I know it's not good for my health. I need to be exercising more. So I'm embarrassed to tell you that I don't do enough. My late wife, we used to grow vegetables in the garden, and she would actually take the leaves and crush them, and we do juicing. And but she's not around, and I am absolutely dedicated to the scientific enterprise. I mean, to dealing with science. It moves my life in a deep way, and in fact, I give emphasis on that to almost everything, even my own good health. So I'm a little bit embarrassed to to tell you that I don't do enough, but I certainly know that drinking water and drinking good kinds of water really important. I know that exercise is important, but I don't do enough of it. So shame on me.
I'm not sure anyone really does enough. There always seems to be a new level that can be reached. But yeah, it's tricky because there are so many different things in life that call to our attention. And it's like, okay, I could spend 1 minute like infusing energy into this water, right? Let's say thoughts or visualizations or whatever, but that's a minute that I didn't spend somewhere else. So